All right, so these are the factoring notes that we did in class on September 24th and 25th. I'm starting with a warm-up that's on multiplying polynomials. Um, we've already done this. So it says the length of a rectangle is x plus 4, so I put an L. The width is x plus 3, put a W. We want to write an equation to find the area of the rectangle. So we know area is equal to length times width. So really we're just multiplying x plus 4 and x plus 3 together. So I'm going to do the box method. And even if you FOIL, you may want to try the box method because when we get to factoring, we'll be using a box. So let's see, we have x plus 4 and x plus 3. Remember, to fill in the box, we multiply. So to fill in this box, we're doing x times x. And keep in mind, these are really x to the first and x to the first. So if we're multiplying, we add exponents. That's x to the second power. For this one, we're doing x times 3, 4 times x, and 4 times 3. So then we just have to list out all of these terms, all of our boxes. I like to circle what my like terms are so I can add them together in my head before I put them down. So let's see, we have x squared. If we add these two together, 4x plus 3x, that gives us 7x. And then plus 12. And we're used to doing stuff like this. But let's say that we start with the area. It says the area of the rectangle is x squared plus 7x plus 12. That's what we got. Let's say we start with the area, but now we want to find the length and the width. Well, that's what factoring is. There's no easy way to go about this. You can't just divide by something or split it in half. You have to actually do a little process here. But anyway, that's exactly what factoring is. So I listed out the steps here for factoring, and I'll admit it's kind of a lot here. So we're just going to jump into an example and kind of follow these steps as we go. So for example 1, we want to factor this function right here. And so it's like this is the answer. We want to figure out what are those two things we multiplied together to get this. That's really the goal here. So the first step is we always want to factor out the GCF, if there's a GCF other than 1. So here, is there a greatest common factor, something I can divide all three of these terms by? And the answer is no. I can't plot an x because this one doesn't have an x. Can't use a 3 because I can't do x squared divided by 3. That doesn't work. So we're just going to go ahead and jump in to the rest of this. If there was a GCF, we always have to pull that out first for this to work out. And I'll show you an example like that when we get to number 3. All right, so filling in these two boxes are pretty simple. The first term goes in the first box, and the last term goes in the last box. So these are the easy ones. Figuring out these two boxes takes a little bit of work. So we're going to start by listing out our A, B, and C values. And you may have heard of this before. We talk about A, B, and C when we work with quadratics. A is always in front of our x squared value. In this case, even though we don't see anything, we know it's really a 1. B isn't always in front of the x value, so that's 6. And C is our constant, so that's negative 27. Okay, so to figure out what goes in these two boxes, it's kind of like a little puzzle. We need two terms that multiply to get us A times C. Well, A times C, that's 1 times negative 27. But the same two terms are going to have to add to get us B, which is 6. And we always use these. We always do A times C right here and B right here. And so this is where you have to think a little bit, because there's only one set of numbers that works for this example, that multiply to get us negative 27, but add to get us 6. And if you're struggling to think of it, you may want to start listing out some factors for 27. And there aren't that many. 9 times 3 should come to mind. But this is negative. So we could do something like 9 times negative 3. And I picked that because if I do 9 plus negative 3, it gives me a positive 6. It's the only set that works. This is the hardest part about factoring, is figuring out these magic numbers. But once you get them, the rest is just we follow the steps. We're going to put these in our remaining boxes. Doesn't matter where I put each one. I can put 9x here or here. And I could have put this as negative 3 times 9 too. I didn't have to put the 9s first. So I'll put 9x here, negative 3x here. Okay, and so now we have our box filled in. We just need to figure out what are these numbers on the outside that we had, multiplied together to get all this stuff in here. We do that by using greatest common factors. So again, it doesn't matter where I start really, but let's start between these two. What's the greatest common factor that both of these have in common? The greatest thing we can divide both of these by, the GCF. And so 1 is a common factor, but they both have x at the very least. It's the greatest thing we can divide both by, so I put that right here. And it doesn't matter where I go next, I can go right here. The GCF between these two, the greatest thing I can divide both of them by, also x. And so you can check this as you go along. X times x gives me x squared. Makes sense, we're doing this right. Okay, let's go over here. Between these two, what's the greatest thing we can divide both by? You may think 3 at first, and that's a common factor, but it's not the greatest common factor. The greatest common factor would be 9. And so we'll put a 9 here. And what determines if this is plus 9 or minus 9 is this box leading out. If this is a positive, I make this positive. If this were a negative, I'd put a minus sign. It's always the one leading out that affects it. So down here, we know it's going to be a negative because the one leading out is negative. And the GCF between these two is just 3. So I'm going to put minus 3. So now we have our factors, x plus 9, x minus 3. And so that's what factoring is. And so if I were to multiply these back together using either FOIL or the box method, I would get this original function. And if I were to factor this function, I would get this answer down here. We could just go back and forth all day. Okay, let's look at the next example, example 2. Okay, so again, I'm going to follow the same process. The first thing we want to check for, is there a greatest common factor that we can pull out of this function? Can't divide 9 and 5 by 2, that doesn't work. Can't plot an x, that one doesn't have an x. So it looks like no, there is no GCF, so we'll just move right ahead. First term is going to go in the first box. Last term, negative 5, will go in the last box. Those are the easy ones to fill in. To fill in these, we first need to figure out what are A, B, and C. So A is always in front of the x squared. That'll be 2. B is always in front of the x. That'll be 9. And then C is our constant at the end, negative 5. So now comes the puzzly part. We need 2 terms that multiply to give us A times C. In this case, A times C, that's 2 times negative 5, so that's negative 10. But these same 2 terms have to add to give us B, which is 9. So you may want to think about this for a minute. You could even pause the video to try to come up with those magic numbers. It ends up being a positive 10 and a negative 1. These multiply to give us negative 10, and these add to give us a positive 9. So those are our magic numbers we're going to put in the remaining boxes. Doesn't matter where I put each one, but I do need to attach an x to them. So I have 10x and negative 1x. And hopefully you realize, even though I didn't put the 1, this is negative 1x. You can put the 1 if you want. It doesn't matter. So now we have our box filled in. We just need to unpack it to get those factors on the outside, the whole goal of this. So let's start here. Let's figure out what is the GCF between these two terms right here. And you may think x at first, and that's part of it, but between the numbers 2 and 10, those are both divisible by 2. So at most, we can divide both of these by 2x. GCF between these two is x. We can check ourselves. 2x times x gives us 2x squared. It's going well. The GCF between these two is 5. And since the one leading out is positive, I'm going to make this a plus 5. And then the GCF between these two is a little tricky. You may think they just don't even have one, but at least they always can be divided by 1. So whenever you think there is no GCF, it's really just a 1. And since the one leading out is negative, we'll make this one a minus 1. So now we have our factors, 2x minus 1, x plus 5. And again, there's a lot of different ways we can check ourselves here. If we want to see if we did this box right, we can just say, it's 2x times 5. 10x is negative 1 times x, negative x. Yes and yes. For this one, is negative 1 times 5, negative 5. Yes. So it's pretty easy to check yourself with this. Okay, let's move on to example 3. So first thing we always want to check for, is there a greatest common factor we can pull out? For the other two examples, we couldn't. For this one, though, we can actually pull out a 2. That's the GCF. That's the largest thing we can divide all 3 of these terms by. So I'm going to pull that out, and we've done this before. You can refer to the GCF notes. So I brought down my signs, and now I have to divide each of these terms by 2. So 2x squared divided by 2, that gets us x squared. 40x divided by 2, that gets us 20x. And then 200 divided by 2 gets us 100. So if we don't take this step and pull out the GCF, the factoring won't work with the box method. So make sure we always do that step. So now we're just factoring the stuff that's inside the parentheses. We're going to let that 2 hang out until the very end, and then we'll go ahead and reattach it. All right, so first box, we're going to put the first term. Now it's going to be x squared. Last term, the 100, will go in our last box. Okay, we can list out A, B, and C. A is going to be 1. There's really a 1 right here. B will be negative 20. And C will be 100. All right, so now we need 2 terms that multiply to give us A times C. In this case, that's 1 times 100. But these same 2 terms will have to add to get us B, which is negative 20. And again, there's only one set that works. So it ends up being negative 10 and negative 10. Multiplies to get us a positive 100, adds to get us a negative 20. So we'll attach an X, stick those in our boxes. And then the last step is we have to unpack the box using GCF. And it doesn't matter where I start. I can start with these two. The greatest common factor between these two is just X. So I'll put an X right here. Greatest common factor between these two is x. You can put that there. Between these two is 10. And since the one leading out is negative, I'll make this negative. And then the greatest common factor between these two, again, is 10. Since the one leading out is negative, I'll make this negative. So now we have our factors, x minus 10 and x minus 10. And now we can go ahead and bring down that 2 that we initially pulled out and just stick it out front. Okay, let's look at this last example. Okay, so you may notice something a little different with this one. We're missing one of the terms that we're used to seeing. So you'll notice there's no x value, which means we don't have a b. We have an a. A is just equal to the 1 that's out front. And we have a c, that's negative 81. But we don't have that b value, so we can consider that to be equal to 0. Okay, so we'll start the same way though. Is there a greatest common factor we can pull out? No. So we'll go ahead and put the first term in the first box, last term in the last box. And then we can try to find our magic numbers here. We need 2 terms that multiply to get us a times c, which is negative 81. But the same 2 terms have to add to get us b, which is 0. So this doesn't work all that differently. It's just now b is 0. It's kind of weird. So the only thing that ends up working is 9 and negative 9. Multiplies to get us negative 81. Adds to get us 0. So we'll attach an x and put those in the boxes. And then again, we'll unpack our box by finding the greatest common factors. So the GCF between these two is x. Between these two, also x. Between these two is 9, and since that one's negative, we'll make this negative. And then between these two, 9 again, and since that one's positive, I make this one positive. So our factors are x minus 9 and x plus 9. And it doesn't matter which one I put first. I could have put my x plus 9 factor first. It doesn't matter. So this example we call difference of squares. I have that listed down here. This may be a little advanced right now. But whenever you see a perfect square minus a perfect square, that is, we can take the square root of this pretty easily and the square root of this one pretty easily. That's difference of squares. So it's always in this form where we have 1 minus sign, 1 plus sign, and then we just take the square root of each term. So the square root of x squared, I'll put that down here, the square root of x squared, that's just x. So that goes up front. And the square root of 81, well, that's just 9, so that goes behind. And so that's how difference of squares always works. So we could have gotten that same answer just by recognizing difference of squares, but also the box method works perfectly fine too. It's just a little bit longer.